So, here we are. We're at the very beginning. There's nothing around us. Don't be fooled by the stuff you can see here. There's nothing around us. No space. There's not even any time. Zilch. But something is about to happen. And that will be the first of all historical events. In fact, what's about to happen is that a universe is about to be created. So, what's the recipe for making a universe? Another great cocktail party question as you're swigging your margaritas. To survive the cocktail, you'll need another non-technical answer like the one I tried to give to earlier questions. So that's the sort I'll offer. 100 years ago, this question would still have seemed the purest metaphysics. How did everything begin? It would have seemed a question beyond evidence, a question that can only be answered philosophically or within religious traditions. Now we have the evidence, and I described some of it in the last lecture, to offer a powerful, rigorous, evidence-based, scientific answer to this fundamental question. And what I want to do in this lecture is look at the outlines of that answer and some of the evidence on which it's based. In the last lecture, I described the origins of modern cosmology and how Western cosmology evolved over 2,000 years. And what we saw was that in the early 20th century, careful scientific work and a lot of observation began to yield a powerful answer to questions that had previously seemed unanswerable, such as how the universe was created. So now I'm going to look at that answer. Okay, so this is clearly, for any attempt like this course in big history at a unified account of the past, this has to be the first question of all. Where did everything start? How did everything start? Where did all the stuff around us come from? The living and the dead, the simple and the complex, our parents, our Aunt Edna, our grandparents, our children. As far as we know, all human societies have asked this question. It's one of the deepest questions one can ask, and every society must have asked it. And they've also offered answers to it. But we also know that most of the answers that were offered in earlier societies were based on very, very limited evidence. And that explains in part why they're so astonishingly variable. But we should not dismiss those answers. They may seem naive to us. Often, embedded in them was a huge amount of good empirical observational evidence. They were rich, they were intelligent, they were based often on as much evidence as a society could muster. And even more important, they mattered. They really counted. And the reason they counted was that they told people who they were and where they were. Imagine a group of people in the Paleolithic sitting around a campfire wondering, how did everything start? Imagine the kids asking all these questions about the stars, about the mountains and so on, and saying, finally, one of them saying, yeah, but how did everything start? Someone is going to have to give them an answer, and that answer, whether we like it or not today, is going to be powerful. So it's very important when we look at the scientific account of origins to also pay our dues to the many other alternative accounts that have been developed in the past. It'll also help us understand the modern answer if we compare it briefly with those traditional answers. So let me try and summarize the types of answers. This is just a very loose summary of the types of answers that different societies have offered to this fundamental question. Here's the first, and perhaps the most common. Traditional answers to the question of the origins of everything often begin with a god or gods. They say the universe was created by a deity or deities. Now, sometimes the gods are a bit amorphous. They sort of lurk in the background, but they're there nevertheless. Here's a passage from a Mayan text that hints at how the gods may always be lurking in the text there, in the back there. This is a very rich text, and I'm just quoting a sentence or two from it. So I hope it just captures the power of the idea of a deity to explain origins. Here's how it goes from the Popol Vuh, the Council Book. Whatever might be is simply not there. Only murmurs, ripples in the dark, in the night. and now a God will appear. Only the maker, modeler alone. And note how this God is a bit like a potter. It's a very, very common image of God as a potter, making the world as a potter makes clay. Only the maker, modeler alone, sovereign plumed serpent. And now the gods seem to multiply. The bearers, begetters, are in the water, a glittering light. They are there. They are enclosed in quetzal feathers in blue-green. Now that's one very common strategy to explaining the origins of everything, to suppose the existence of a God. But there's a problem with it, of course. You can imagine a bratty kid at the back of this group who's discussing the origins of the universe saying, yeah, but who made God? Who made the modeler? Who made the guy in the quetzal figures? And this is actually a very deep question. It's always going to be there. And I suspect most people in most societies were aware of, at the back of their minds, that there was this dilemma. Who made God? Okay, a second strategy. These strategies aren't separate. They often overlap, as we'll see. Many creation stories posit a sort of initial chaos, out of which something emerged. Now, the word emerged is very appropriate here. I've talked about emergence, the way that out of chaos something new can emerge. And I think something similar is going on in these stories. Here's a source. It's the Rig Veda, the basic Hindu scriptures, which were probably written down about 3,200 years ago. And once again, I'm just picking a tiny passage from a very, very rich religious tradition. Here's how it goes. There was neither non-existence nor existence then. What we're talking about is a sort of state in which there's not quite nothing, but there's not quite something. The sort of potential. That, in fact, is very like modern accounts of the vacuum. There was neither non-existence nor existence then. There was neither the realm of space nor the sky which is beyond. What stirred? Where? In whose protection? Can you see how a sort of conscious being of some kind seems to be creeping into the story? There was neither death nor immortality then. There was no distinguishing sign of night nor of day. And then we get very clearly the idea that lurking somewhere is a conscious presence, a deity of some kind. That one breathed, windless, by its own impulse. I love that phrase, and I think it captures very beautifully the difficulty of explaining origins. So that's another strategy. The universe emerged out of a primeval chaos, perhaps with a nudge from a god. Many creation stories talk about a birth from egg. Some accounts describe the universe as a sort of living organism, which, like living organisms, was born from a parent or from a sort of cosmic egg. Note the analogy with Lemaitre's idea of a primeval atom. And then another alternative is to think of the origins of the universe as a sort of awakening. This is poetically, perhaps even a deeper idea. There are many traditions that describe it as a sort of awakening, but here too you'll find there always seems to be a god lurking in the background. Here's a story from the Kararu people of South Australia. Inside a deep cave below the Nullarbor Plain slept a beautiful woman, the sun. The great Father Spirit, this is where the god appears, of course, the great Father Spirit gently woke her and told her to emerge from her cave and stir the universe into life. The Sun Mother opened her eyes and darkness disappeared as her rays spread over the land. She took a breath and the atmosphere changed. The air gently vibrated as a small breeze blew. It's a lovely image. Okay, now let's move on to the modern account of origins. One of the things the modern account doesn't do is posit a divine creator, and it does so very, very systematically and very deliberately. And there are two real reasons for this. The first is one we've already seen. If you posit a creator, you may be not solving your problem of creation, but actually simply creating a new one. There's an infinite regress. You have to explain the creator, you have to explain how the creator of the creator was created, and so on. But there's a second problem with deistic accounts of the origins of the universe. There's no evidence. Science knows of no evidence-based way of showing the existence of a creator God. So this is something, even if you believe in such a God, you cannot talk about that God in terms of science. Nevertheless, the modern account of origins faces the same problem that all creation stories face, and I'll call that the paradox of beginnings. Who created God? Who or what laid the egg? How can you get from nothing to something? And quite frankly, the modern account of creation has no better solution than any other story. We just don't know what there was before the Big Bang. We don't even know if time or space existed. It's actually characteristic of science, unlike some forms of institutionalized religion, that it admits its ignorance at this point. Most cosmologists will say, we reach a point where we can say nothing more. Now, cosmologists are also human, and this means that many of them actually are desperately trying to think their way through this puzzle. Stephen Hawking has famously suggested that perhaps the question's a bad one. Perhaps we're simply getting caught in a bad question. If the universe, if the geometry of time-space, of space-time, is actually circular, then to ask what there was before the beginning is as ludicrous as to ask what is north of the North Pole. Perhaps it's a silly question. Others are pursuing different directions. You may be aware of the fact that at CERN, on the Swiss-French border, they're building the Large Hadron Collider, which will be the largest particle collider ever built. CERN is the European Organization for Nuclear Research. The Large Hadron Collider will be a 27-kilometer-long circular tunnel. It's running under the French-Swiss border. It's designed to smash particles together with almost as much violence as during the Big Bang. In other words, to take us back to the conditions of the Big Bang and to see what happens. This is evidence with a vengeance. We may actually get new evidence about what happened at that moment. So watch this space. It'll be interesting. Okay, so at the beginning, the modern account of creation is really as arbitrary as any other. We just don't know. Then, from a tiny, tiny fraction of a second after the moment of creation, we can tell, and this is itself quite remarkable, we can tell a well-grounded, scientific story based on masses of carefully tested evidence. It begins 13.7 billion years ago. Now, to explain this story, I'm going to need some very, very large and very, very small numbers, for which we'll use exponential notation. So let me briefly explain what I mean, how exponential notation works. Some of you will be very familiar with this, but in case you're not, let me try and explain it briefly. You remember powers of 10. I talked about that in the second lecture. It's a similar sort of principle. A figure 1 with 2 zeros after it is 100. That represents 2 tens multiplied together. The figure 1000 with 3 zeros represents 3 tens multiplied together. So in exponential notation, what we do is we write 10, and then we put a tiny superscript 2 for 100, and 10 to the 3 for 1,000. That means 10 multiplied by itself 3 times. 1 million is 10 to the 6 on the same principle. Now we can do the same with fractions. 1/100th is 0.01. It's 1/10, 1 over 10, multiplied by itself twice. So 1/10 multiplied by itself. So what they do is they write 10 to the minus 2. That means instead of 10 multiplied by itself, it's 1 over 10 multiplied by itself. 10 to the minus 3 is 1,000th, and so on. So I hope you've got the basic principle of exponential figures, because now I'm going to start using them. Okay, now, imagine we're back at that campfire. I'm a modern scientist trying in very simple language to explain what actually happened. Here's the story. At the very beginning, we can't say anything. So our story is going to start 10 to the minus 35 of a second after the moment of creation. Yes, that's a decimal point followed by 34 zeros with a forlorn 1 later. It's that small a bit of a second. From that moment on, we can tell a good scientific story. So, just before that, something appeared. What can we say about this thing that appeared? Well, it was tiny. It was probably the size of an atom. It was also inconceivably hot. Think as many gazillion centigrade as you like, and you're probably not there yet. The other thing we know about it is that it's expanding very, very rapidly, like a sort of huge explosion. And that was the point of Fred Hoyle calling it the Big Bang. And as it's expanding, it's cooling. So already we know quite a lot about it. It's tiny, it's very hot, it's expanding, and as it's expanding, like every expanding gas, it's cooling. At the very beginning, matter and energy are indistinguishable. It's a sort of mishmash of stuff and forces and things. Then what we'll see happening is that out of this mishmash, distinct things start to appear. It's as if through the fog we can start to see clear things. It may help to think of phase changes. A phase change occurs when steam cools and turns into water. Steam gets cooler, 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 then suddenly, at 100 degrees centigrade, it turns into something else. It turns into water. Now, a whole series of phase changes, a bit like that, happened in the early universe as it cooled. Things and forces appeared. Gravity appeared. And the strong and electromagnetic forces, and also the fourth fundamental force, the weak nuclear force. Now, I'm not going to talk about the weak nuclear force. We don't need it. I don't want to go there. But the four fundamental forces appear. The strong force holds the nuclei of atoms together. The electromagnetic force holds atoms together because it holds particles with opposite charges together and drives apart particles with the same charge. It drives electricity and magnetism. Now something quite bizarre happens, and it's not the only bizarre thing happening. It's known as inflation. From, now another figure, 10 to the minus 33 to 10 to the minus 32 of a second, the universe expands much faster than the speed of light. Now, even the non-scientists amongst you will have heard that nothing can move faster than light. So what's going on? Well, what's happening is nothing is necessarily moving faster than light. The fabric of space-time itself is expanding faster than the speed of light. And the universe grows from the size of an atom to the size of a galaxy. So this phase is known as inflation. Then something else bizarre happens. And remember, we're still in the very early moments of the first second of the universe's history. Particles start to appear out of the murk, quarks, which are what protons and neutrons are made from. And they appear in opposite forms. And when these forms meet, they annihilate each other. So a huge amount of matter appears, and then immediately it annihilates itself, releasing energy, according to Einstein's formula, E equals mc squared. And what this means is that of all the matter created in the beginnings of the universe, only perhaps something like a billionth remains. So all the matter around us seems to consist of about a billionth of the matter created in the Big Bang. The rest was annihilated in this bizarre game of subatomic musical chairs. Okay. It leaves just a few survivors, this game, and these forlorn survivors form protons, which are positively charged, and neutrons, which are electrically neutral, and they will form the core of atoms. Electrons also form. They're lighter than protons and negatively charged. They play the same game of musical chairs as electrons with positive charges annihilate electrons with negative charges, leaving just 1/billionth of all the ones that are created, and the rest goes in a flash of energy. Now let's move forward. A few minutes after the Big Bang, what does the universe look like? Well, it's now bigger than a galaxy. It consists of a hot plasma. That is to say, a mixture of energy and charged subatomic particles. It's a bit like the center of the sun. Because the universe is so hot, particles and energy are moving fast and interacting violently. The particles, the subatomic particles, they're all charged. They all have electrical charges. The whole universe is sort of sparkling. Energy and matter have sort of separated, but not yet completely. Now we move on 380,000 years, okay? And we come to the next crucial episode in the story, the next crucial phase change, if you like. Suddenly, at a certain point, at a certain temperature, a lot of things change. And this is what happens. The universe is now cool enough so that protons with positive charges can capture electrons with negative charges, and they form simple atoms of hydrogen and helium. Now, atoms are neutral because the two charges cancel out. So imagine all the matter in the universe suddenly turns into atoms and goes electrically neutral. And now energy and matter are more separate than they've ever been before. In fact, energy can now flow through the universe freely without getting entangled in the charges of these loose subatomic particles. And early Big Bang theorists hypothesized that at that point there would be a sort of flash of energy. Now what happens? The universe cools. It enters what we can think of as a sort of dark age that may have lasted several 100 million years. If you want to try and imagine it, though honestly there's a lot of guesswork here, you should probably imagine empty space with a very, very faint glow of energy through it. Now, that's a very simple attempt to capture the modern story of creation. I hope you'll agree that in some ways it's quite as strange as any creation story you can find in any culture. And we also have to say one other thing about it. Scientists are very confident that most of what they say is about the origins is more or less accurate. It's evidence-based. But there's a lot we don't know. Let me just give you one powerful illustration. We know that there's a lot of stuff out there that we know nothing about. This is known, the scientists call this, because I can't think of anything better to call it, dark matter or dark energy. We know it's there because studies of the movements of galaxies show that the stuff out there that's exerting a powerful gravitational pull. But we can't figure out what it is. We can't identify anything associated with that stuff. And yet this stuff may account for up to 95% of the universe's total mass. Now think how bizarre that is. What we're saying is that we seem to understand only 5% of the universe. Now that's the downside. We have to admit that our understanding is still fairly limited in that area. There's a lot of the universe we don't understand. But now we're going to put that aside and carry on with the story. Of that stuff, by the way, 70% may consist of undetected forms of energy, and 25% may consist of matter in forms we can't detect because they don't emit radiation, such as cold, dead stars or planets, or perhaps because they're too small, such as the subatomic particles known as neutrinos. Again, watch this space. There's exciting science going on. CERN experiments could clarify some of this. It's the sort of thing in which there could be very important developments in the near future. Okay. Now what I want to do is look at the evidence. Why should anyone believe this weird story? And the answer is because, like all the strong claims science makes, it rests on a colossal amount of carefully tested evidence. And what I want to do is just briefly describe some of the main pieces of evidence. And I'm going to describe 5 main pieces of evidence. Okay, first piece of evidence for the Big Bang, the red shift. And I've already described this. As we saw, Hubble used the idea of the red shift to show that the further away an object was, or rather, the most remote objects in the universe seemed to be traveling away from us, and the further away they were, the faster they were traveling away. And the red shift, you'll remember, is the fact that absorption lines on stellar spectra sometimes seem to be shifted towards lower frequencies, towards the red end of the spectrum. And that's interpreted as a sign that they're moving away from us. It's a Doppler effect. Now, this evidence meant that the universe must be expanding. If it's expanding, at some time in the past, it was infinitely small. That's the first and most powerful, well, perhaps not the most powerful, but one of the most powerful pieces of evidence for Big Bang cosmology. I qualify that because it actually took 20 years or more before cosmologists began to take this idea of a Big Bang seriously. The second piece of evidence is the cosmic background radiation, or CBR. And it's this piece of evidence that really clinched Big Bang cosmology in the 1960s. It's slightly technical, but I'm going to try and describe it in non-technical language. Until 1965, Big Bang cosmology had a rival theory, the steady state theory, and this was supported, amongst others, by Fred Hoyle, who we've met before, and who was to become one of the great outspoken opponents of Big Bang cosmology, and opposed it throughout his life. Hoyle and his colleagues argued that the expansion of the universe was caused by the continuous creation of new matter. This was a process that had been simply going on forever, matter's always being created in the middle of the universe. Now, you've got two rival theories of the origins of the universe. The scientific question to ask is, how can we discriminate between them? And supporters of Big Bang cosmology had an idea about how you can tell the difference between them. You remember that about 380,000 years after the Big Bang, I said that matter and energy finally separated as matter became electrically neutral. And theorists argue there must have been a sort of flash of energy at this point, and it ought to pervade the entire universe. And they argued it should still be detectable as a very, very weak energy source coming from all parts of the universe. If it could be detected, they argued, it would prove their theory right. But how could you detect it? How can you discriminate between these two models of the universe? Well, it turns out it was found more or less by accident in the middle of the 1960s. In 1964, two engineers, radio engineers, Arno Penzias and Robert Wilson, were trying to construct an extremely sensitive radio antenna to detect signals from satellites. They wanted to eliminate all background noise so they could hear signals, the signals they wanted, very, very clearly. And as they tried to eliminate background noise, they found there was a persistent sort of hum in the background that they couldn't get rid of. They tried everything. At one point, someone said, I should say that the antenna was a horn-like apparatus. Someone said, I think there may be pigeons roosting there. And as any scientist knows, pigeon droppings are matter. They are not at absolute zero, so they're emitting radiation. So perhaps this was the sort. So they clean out the pigeon droppings, and it's still there, that hum. And then eventually someone said to them, this is actually what was predicted by Big Bang cosmology. There ought to be energy coming equally from everywhere in the universe, everywhere you look. And that clinched it, because no other theory could explain this astonishing fact of energy coming at you, not from a specific point in place, so you can say it's coming from that galaxy or this star, but from everywhere. And that's what really clinched Big Bang cosmology and made it the central idea of modern cosmology. Now, very briefly, I want to list some other pieces of evidence in support of the theory. One is just the age of the universe. So this is the third piece of evidence. Big Bang theory predicts that we can estimate the age of the universe, and the estimates now are about 13.7 billion years. No object has ever been found that's older than 13 billion years. If the universe was in fact infinite, this would be very bizarre indeed. But of course this fits very well with Big Bang cosmology. If the theory is right, then the young universe ought to have looked rather different from today's universe. Above all, it ought to have been more compact. Things should be closer together. And if you look over huge distances in space, say you look 12 billion light years into space, in effect, you're looking 12 billion light years away. So you can see what the early universe was like. And when you look at it, you find that indeed it is rather different from today's universe. With cosmology, unlike any other historical discipline, we actually have time machines. We call them telescopes. That's the fourth bit of evidence, and the fifth is the chemical makeup of the universe. Big Bang cosmology predicts that in the Big Bang, huge amounts of hydrogen and helium were made, but there was no time to make any elements more complicated than that. It predicts that something like 3/4 of the early universe should consist of hydrogen and most of the rest of helium. And that, in fact, is exactly what you see when you look out at the universe. So for these reasons, despite this bizarre story, Big Bang cosmology offers a scientific, well-tested explanation of how the universe was created. However, this early universe didn't yet contain anything of much interest. How can you get something more interesting in such a universe? That's the question we pursue in the next lecture. Thank you. You'll need another non-technical answer like the one I tried to give to earlier questions. So that's the sort I'll offer. 100 years ago, this question would still have seemed the purest metaphysics. How did everything begin? It would have seemed a question beyond evidence, a question that can only be answered philosophically or within religious traditions. Now we have the evidence, and I described some of it in the last lecture, to offer a powerful, rigorous, evidence-based, scientific answer to this fundamental question. And what I want to do in this lecture is look at the outlines of that answer and some of the evidence on which it's based. In the last lecture, I described the origins of modern cosmology and how Western cosmology evolved over 2,000 years. And what we saw was that in the early 20th century, careful scientific work and a lot of observation began to yield a powerful answer to questions that had previously seemed unanswerable, such as how the universe was created. So now I'm going to look at that answer. Okay, so this is clearly, for any attempt like this course in Big History at a unified account of the past, this has to be the first question of all. Where did everything start? How did everything start? Where did all the stuff around us come from? The living and the dead, the simple and the complex, our parents, our Aunt Edna, our grandparents, our children. As far as we know, all human societies have asked this question. It's one of the deepest questions one can ask, and every society must have asked it. And they've also offered answers to it. But we also know that most of the answers that were offered in earlier societies were based on very, very limited evidence. And that explains in part why they're so astonishingly variable that have been developed in the past. It'll also help us understand the modern answer if we compare it briefly with those traditional answers. So let me try and summarize the types of answers. This is just a very loose summary of the types of answers that different societies have offered to this fundamental question. Here's the first, and perhaps the most common. Traditional answers to the question of the origins of everything often begin with a god or gods. They say the universe was created by a deity or deities. Now, sometimes the gods are a bit amorphous. They sort of lurk in the background, but they're there nevertheless. Here's a passage from a Mayan text that hints at how the gods may always be lurking in the text there, in the back there. This is a very rich text, and I'm just quoting a sentence or two from it. So I hope it just captures the power of the idea of a deity to explain origins. Here's how it goes from the Popol Vuh, the Council Book. So, here we are. We're at the very beginning. There's nothing around us. Don't be fooled by the stuff you can see here. There's nothing around us. There's no space. There's not even any time. Zilch. But something is about to happen. And that will be the first of all historical events. In fact, what's about to happen is that a universe is about to be created. So, what's the recipe for making a universe? Another great cocktail party question as you're swigging your margaritas. To survive the cocktail, you'll need another, but we should not dismiss those answers. They may seem naive to us. Often embedded in them was a huge amount of good empirical observational evidence. They were rich, they were intelligent, they were based often on as much evidence as a society could muster. And even more important, they mattered. They really counted. And the reason they counted was that they told people who they were and where they were. Imagine a group of people in the Paleolithic sitting around a campfire wondering, how did everything start? Imagine the kids asking all these questions about the stars, about the mountains and so on. And saying, finally, one of them saying, Yeah, but how did everything start? Someone is going to have to give them an answer, and that answer, whether we like it or not today, is going to be powerful. So it's very important when we look at the scientific account of origins to also pay our dues to the many other alternative accounts